So let's see where we stand. So we treated the Bose gas, and specifically we calculated the average number of particles, which is the only thing that we can measure probably in this Bose gas. Again, particles are bosons. We treat the grand canonical perspective from the grand canonical ensemble. Grand canonical ensemble. We do a specific trick. So we calculate everything, and eventually we switch between the number of particles and the chemical potential. Now, why do we do that? Well, otherwise we cannot proceed mathematically. But there is a one-to-one, okay, one-to-one connection between mu and n. Therefore, we can switch between them at the final stages. For n, we obtained the following interesting result. Where it is. So n was G0. G0 is our degeneracy. V lambda t to the power 3, and the polylogarithmic function of the fugacity. Okay. What is lambda t? Lambda t, I will write it to you over here, is a square root of 2 pi h bar squared divided by m k Boltzmann t. And f alpha of the fugacity is the summation I goes from 1 to infinity, fugacity to the power I, 1 over I to the power alpha. Fugacity is e to the power beta mu. So this is what we obtained, and there was a problem. Why there was a problem? I remind you. The problem was with this function, this polylogarithmic function. So we plotted this f3 halves of the fugacity as the function of the fugacity. It diverges, or basically not converges to anything, for fugacity larger than 0, larger than 1, which means mu equals to 0 exactly. This is 1. But it not diverges at 1, it reaches a specific point. Okay. This point is 2.3 something. Okay. Now that was a problem. Why it was a problem? Because look at this correspondence. Okay. I remind you, the problem is this is finite. Okay, this is finite. It's bounded. N is unbounded. V we can control. Temperature is in control. So the major problem is that N divided by V G0 lambda t to the power 3, okay, equals to f3 halves of the fugacity. Now, this is bounded. This is unbounded. Right-hand side cannot be larger than 2.3. Left-hand side we can make as large as we like. We can push a lot of particles into the system, etc., etc., etc. So this is the problematic point. Okay. At some point, something bad happens to the system, okay? And whatever we have developed is ruined. And we found a solution to this paradox. And the solution to this paradox was the following. So we had the average number of particles or the incubation number of particles for each level, energetic level in our system. And we sum them up, right? So because they are discrete, in order to compute the total number of particles inside the system, we went and for each epsilon we counted what is the average number of particles per state. The states are independent, so we counted them all. We couldn't count. Why we couldn't count? Because we don't know how to count and sum up discrete sums. So we transferred everything to an integral. And this integral, was our average number of particles. Okay? And the problem, eventually what we found. What was the problem? The problem was that when the temperature is low enough, okay, therefore this bound occurs, what happens at epsilon, at the lowest, at the ground state, is that the number of particles that are sitting over here is beginning to grow. Grows and grows and grows and grows and grows and grows and grows. It actually grows indefinitely, right? So if you remember, we had an approximation for this unbound growth. It was this n0 was approximately k Boltzmann T divided by epsilon 111 minus mu. Okay, and n1, which is what the average number of particles at the excited state, was there it is. I don't remember what it was. So it was k Boltzmann T. It was k Boltzmann T epsilon 111 minus mu plus epsilon 111, I'm sorry, epsilon 211 minus epsilon 111. Okay? So we look just on those two numbers. Now mu can approach to epsilon 111 as close as possible. Okay? Nothing prevents mu to be lower than epsilon 111, but as close as possible. On the other hand, n1 is always bounded. Why? Because, well, this number can go to 0. Right? This can't go to 0. But the other number, this one, can't go to 0. There is always a lower bound on this difference over here. So basically, n1 is bounded. n0 is unbounded. So what happens? If we have a large number of particles inside our system, and we lower the temperature, at some point, the majority of the particles, or I won't say a majority, at some point a macroscopic portion of the particles will sit at n0 over here. Okay? And then there could be some other particles that sit at n1 and at epsilon 111, at epsilon 211, etc., 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 etc. Okay? But there is a macroscopic portion of the particles that are sitting at a microscopic state. Now, when we integrate, the contribution of each epsilon is completely negligible. Meaning that what we learned in our first year, that you can cut a single point, right? If you cut a single point out of your integral. Okay. Say, well, I'm integrating up to here, and from here on. The contribution of a single point or a single epsilon is always negligible. Okay? That's our assumption. Now what happens here is the opposite. The contribution of a specific epsilon, it's not negligible, Okay? So it has to be considered. The following question, yes, you can say, well, Stas, great. So this is only state. The lower the ground state, what happens at the next excited state? This argument comes in. This is unbounded, and it shields all the other states from over-occupying. Okay? So if there is a place, like a huge black hole, where you can pour more and more and more particles, and they're going to stay over there, it's the ground state. What happens to all the other excited states? They're protected. They have a bound. So you cannot push there too many particles. This is not the case for the ground state. So you have to take into account this very special property of the ground state to accumulate huge number of particles over there. Unbounded number of particles that won't happen to all the other states, right? Simply won't. So in all our calculations, we haven't included this additional state. Okay? And the solution is actually quite simple. What the solution? The solution is, this is correct. All of this is correct. But above a specific temperature. Okay. Meaning, there is a temperature, T, larger than Tc. When this is fine and everything is great, right? Now, but there is also a temperature T smaller than Tc, when the average number of particles, it's what? It is whatever we computed over here. So let's call it N excited. So you compute all the contributions for all the excited states, plus N0. Okay. And you have to take into account N0 specifically. You cannot throw it away. You cannot say it's negligible. You cannot say I'm computing an integral and everything is continuous. So contribution of a single point is completely negligible. It is not true. Physically not true. Okay. So the only correction is what? The only correction is add N0 over here. What is N0? Well, we know this. We know that it is 1 over e to the power minus beta, beta epsilon 0 minus mu, minus 1. Now epsilon 0 equals to 0, right? We can always set our ground state to be the lowest state. So we obtain that N0 equals to 1 over e to the power minus beta mu minus 1 equals 1 over psi minus 1 equals to fugacity divided by 1 minus fugacity. Question, yes?
Why can't I, in higher temperatures than T critical, add as many particles as I want?
You can, but they will spread out everywhere. Right? So the problem is as follows. You have a critical temperature. Now, so your connection is this thing. G0 V. Sorry, it's a bad marker. The question is not why, is what is the critical temperature? So you have G0 V divided by lambda T to the 3 F 3 halves C, right? And I'm saying that it equals to N. It's not the average number of particles, because what we do, we have the switcher. We say we do not control mu, we control N. So set this guy to a constant. You choose it. And out of here, you can compute what is the critical T.
each temperature I have a different critical.
Exactly.
For each number of particles I have a different.
For each number of particles, you're going to have a different critical temperature. It's not a phase transition per se, because phase transitions, we will return to phase transitions. Phase transitions occur due to interactions. Here, it's the mathematical meaning of what you have. Okay.
So when you said that, then
What is, wait. So let's compute the TC. Okay. Can we compute the TC? Okay. So what is the TC is going to be here? So we say the following. At TC, we know, so at TC, C goes to 1. Why we want C to go to 1? Because we want to bound the right-hand side by this number 2.312, etc. Okay. So at TC, this goes to 1. So we have G0 V lambda TC to the power 3 multiplied by 2.31 whatever. Okay? On the left-hand side, you have your number of particles, which is n. Okay? So we obtain that lambda at TC equals to the power, it was 3? 3, yes. Lambda at TC, it equals to G0 V 2.31 divided by n to the power of 1/3. Now lambda TC, it is this guy, right? So we know that 2 pi h bar squared divided by m k Boltzmann TC, okay, to the power of 1/2. Okay. So out of here, we obtain that TC, okay, TC equals to, well, it's an ugly expression, but it's still true. So we have n n divided by G0 V 2.31 to the power of 2/3, yes, 2/3, multiplied by 2 pi h bar squared divided by m k Boltzmann. So in this perspective, it's going to depend on n. The problem is, what is your chemical potential? For any given n, you have a correspondence between the chemical potential and the average number of particles. It depends on your temperature. Okay. Now, the thing is that because of the restriction on the right-hand side, for any temperature, if you push there enough particles, something's going to break. And this breaking occurs at the ground state, first of all. And the moment it's broken in the ground state, that's it. Okay. Now, it depends, as you see, on the number of particles. Okay.
So in last lecture, you said on a specific element, I don't remember which, that the critical temperature is 3 Kelvin. What does it mean?
It depends on how many particles you pushed inside. We had a specific density of particles. Okay. You need a specific density of particles. I also said, well, what is the density of particles in a liter? Okay. So, to perspective, it's different from the phase transition that you encountered before, but the idea is something critical happens over here. Now, the criticality previously happened because many particles are somehow connected to each other, they've done something to each other, etc., etc., etc. Here, the phase transition is different. The perspective is, all the particles, they do not interact, but they all want to sit, they prefer to sit, at the lowest possible energy, right? And you cannot simply say, well, I integrate this out. You can't, okay? Therefore, you have to go to this two descriptions. above the critical TC, this is the number of particles, the average number of particles that you have in your study system. Below, you by hand have to put this additional N0. Mathematically, why you have to put it? Because you're looking on the N0 not as a continuum contribution, but as a delta function contribution. Okay? This is, and when you integrate this delta function, you have this N0 over here. Now, what is N0? Well, it's fugacity divided by 1 minus fugacity. That's it. Now, everything else works just fine. Now, what are the properties of this so-called phase transition? The Bose-Einstein condensation, because what happens over here at Tc at T equals to Tc, Bose-Einstein condensation occurs. It is, you cannot simply say that whatever happens in my system is due accumulation of many events, right? So because what we have done before, in order to compute the average N or the grand canonical potential, we have summed over all possible energetic states, right? And each energetic state contributed something, but it was part of the continuous spectrum. Okay? So here, this is simulation. Accumulation of many events matters. Here, it's, well, yes, it's many events, but there is also one singular event that contributes. And the contribution of this one singular event, it's not negligible. This is the whole difference. Previously, pick any energy, kick it out of the system, the result is going to be still the same. Okay? Here, yes, you can do it for any energy, but not for the ground state. You cannot kick out the ground state out of the system. You can do it over here, and you cannot do it here. Why? Because the contribution is not negligible. Okay? So, a lot of events, it's the power of the many that matters. Here, it's the power of the one. Okay? That's the main difference. Now, that's great that we have n and n. What the more meaningful concept or the function that we can use in order to compute everything else is not n, it's something else. What is this something else? The grand canonical potential. And I can ask the question, what is the grand canonical potential? Because if I know the grand canonical potential, how we obtain this? By taking some specific derivative of n. If I want to compute the average energy, if I want to compute the pressure, if I can compute something else. Okay, so how do I operate? I take the thermodynamical potential, in this case, the grand canonical potential, and then take a specific derivative that's related to this quantity that I want to compute. Or either I go to computing all the probabilities, etc., etc., etc. Okay, so what is psi? So how I compute psi? Do you remember?
Partition function.
The partition function. But if I know n, so n is known.
You can do an integral.
I can do an integral, right? Because what is n? It's minus d psi d mu. Okay. So I know that psi is minus an integral of n d mu plus some constant. And we usually don't really care about constants because, like in energy, all the thermodynamical potentials are all defined up to a specific constant. So let's forget about this for a second. It's a constant, so. Okay, so I have to take an integral out of this guy. Okay, so let's do an integral out of this. So minus an integral of g0v divided by lambda t f3 halves
lambda t to the power of
3, you're absolutely right, of the fugacity, d mu. Now, it's not fugacity because we are integrating with mu, so it is e to the power beta mu. Okay, so what do we have over here? So we have minus. Let's take everything out. So we have g0v lambda t to the third and have an integral. Now instead of the polylogarithmic function, we will write it down as a representation of this sum. So it is a summation. I goes from 1 to infinity of e to the power beta mu to the power of I and I to the power 3/2 d mu. We use the usual trick of physicists. We switch the order on integration and summation, and we usually hope that it works. So it is minus g0v lambda t to the third. And here we have a summation. I goes from 1 to infinity of 1 over I to the third 3/2, an integral of e to the power beta mu I d mu. Okay, so the next step, what is the integral of e to the power beta mu I d mu? It is 1 over beta I to the power multiplied by the exponent e to the power beta mu I. Okay, so I plug it inside. So psi equals to minus g0v divided by lambda t to the third power, a summation of I goes from 1 to infinity of 1 over I to the 3/2 multiplied by 1 over beta I e to the power beta mu I. That's it. So we take beta out. So g0v lambda t to the third power k Boltzmann t, summation I goes from 1 to infinity e to the power beta mu I divided by I to the power 3/2 plus 1, so it's 5/2. 5/2. Okay, we can say that this is minus g0v divided by lambda t to the third k Boltzmann t, and here is the polylogarithmic function of the 5th half order, or the fugacity. Okay. Very nice result, but when it holds, so t larger than tc. And what happens when t is smaller than tc? I have to add the n0. Okay. So when I can say that for t smaller than tc, psi is psi excited plus psi 0. What is psi excited? Psi excited is minus gzv lambda t to the third k Boltzmann t f 5/2 of what? Of 1. Why 1? Because we crossed to the situation where we had to where we had to use the contribution of the singular ground state. Okay? Now, when it happens when the fugacity is almost 1. Okay? So I don't go here and say 1 minus something. I don't use this approximation. I'm just saying that it's 1. The fugacity is 1 in this limit. Okay? Great. And the next one, we have to add the integral of d mu of what? Of e to the power beta mu divided by 1 minus e to the power beta mu. Okay, so let's compute this integral over here. How we compute it? So let's say that 1 minus beta mu, 1 minus e to the power beta mu equals to x. Okay, so what we know that d of 1 minus e to the power beta mu equals to dx. So dx equals to minus beta e to the power beta mu d mu. Okay. So what we have is that psi equals to minus g0v lambda t to the third k Boltzmann t f 5/2 of 1 plus k Boltzmann t, and here I have an integral, right? An integral of what? 1 over x dx, okay? Which is minus g0v lambda t to the third k Boltzmann t f of 5/2 of 1 plus k Boltzmann t of log of what? Log of x. Log of x. And x is 1 minus e to the power beta mu. Okay. This is the ground canonical potential. Now, from now on, if we wish to compute anything, we take the specific derivative above, below PC, or above PC, and anything that we like is obtained out of those derivatives. Okay? Now, actually, it's somehow easier to work with the number of particles and not take all those derivatives again and again and again. But let's see. So the first question that I want to ask you is as follows. What is the, or how, the average number of particles behaves with the temperature below the critical temperature, or anywhere. So, what is N0 average divided by N as a function of temperature? Right. Now, it's important to ask this guy because otherwise nothing will work. We need to work in the limit of many particles. Otherwise, you don't see any transition, you don't see anything. Because, well, if you look on 3 particles, it's okay that there are going to be 2 particles sitting in the ground state. Doesn't matter. So, yes.
Stas, shouldn't there be in our calculation of the ground canonical potential the energy factor in the?
It's plus a specific constant.
No, like in the integral of e if the fugacity minus what?
What? It's only for the ground state. What is the energy of the ground state?
It could be 0. It could not be 0.
It is 0. In our case.
Oh, okay.
Okay. It is a spectrum of what? Of kinetic energies. And I can also set the ground state as 0, right?
And also, if the chemical potential is equal to 1 to 0, then shouldn't the natural logarithm diverge?
Oh, interesting question. So why can I say that it's 1 over here? Yes, but I cannot say that it is 1 over here. Right? I'll point out the question. I calculated something and I had this f to the 5 halves and said, well, here fugacity sits, right? Here fugacity sits. This fugacity, I am saying it's 1. But at the same time, okay, I'm using all this fugacity, and I'm not consistent. I'm not putting 1 over here. Okay? What's happening over here? Now, the answer is, well, it's not exactly 1. It's always little less than 1. But it's very close to 1. Okay? It's close to 1. Now, when I look on f to the 5 halves as a function of the fugacity, it behaves in the following fashion. It grows, it reaches a specific point, which is not 2.6, 2.3, it's actually 1.6, okay? In this vicinity of 1. So, if I'm a little bit less than 1, let's ask the following question. If my fugacity is very close to 1, but it's not 1, okay? It's over here. It's 1 minus delta, okay? Then it is not f 5 halves of 1, it is f 5 halves of 1 minus a small number, which is somewhere over here, right? But it's still extremely close to this 1.6. So if I'm approaching this limit where the fugacity is 1, but I'm still below, I'm approaching the limit of 1.6. So I neglected something extremely small, okay? In this case, okay? So I didn't neglected something, but it's small, not large, something very small. Now, if I'm looking on the log of 1 minus beta mu, can I just simply say it's 1? Because I'm going to neglect or introduce something that is extremely large. Okay? This is why it's forgivable, okay, and possible to neglect the corrections in these functions, but because they are extremely small, but it's impossible to simply say, oh, it's 1 and that's it, or then 0, because exactly where it's 1, it diverges. All right? So it is a consistent approach. You can say, Stas, you said this is 1 over here and it's not 1 over here. Where is this? But I'm absolutely right, because I can neglect the other stuff. And I cannot neglect if I introduce infinity. Okay? I cannot introduce divergency, but I can throw out some very small numbers. Any other questions? Let's go back to our original idea. Because a lot of stuff is actually based on this guy. Okay? And it's not just for any n, and work in the limit when average n is going to infinity, which is called the thermodynamic limit. Okay? I'm looking on a system where there is a macroscopic number of particles, not 7, not 10, not 100, but 10 to the power 20. All right? Real physical system. Okay, so what happens in this system? Remember, we want to compute the average number of particles, and it's related to your point over here. All right, so the only thing that I want to do is to take d psi to d mu, take the minus sign, and I obtain the average number of particles. Above the critical TC, below the critical TC, doesn't matter. This always holds. Okay? This always holds. This always holds, doesn't matter. So I can compute everything. The problem, and it's related to your question, is that I neglected something, right? I neglected some small stuff over here. Here I have not introduced divergency. It's still fine because, well, the only thing that I neglected are something which is very, very small, and I take derivative of this as something very, very small. It's not going to contribute anything. The other problem, which is a crucial problem, well, in order to answer this, I somehow need to tell you how this mu, okay, it's behaving below the critical temperature and above the critical temperature, okay? This is something that I have to tell you. Otherwise, I cannot answer this question because the T is modified or going to be modified in this equation. When T is modified, the chemical potential is also modified because I fixed the total number of particles to be constant, right? A specific number. So mu is going to be modified as well. Okay, so usually I modify beta, something stays constant, and stays constant, mu have to be modified. How mu depends on the temperature? I don't know. I should solve something. But you remember, and it's also already occurred to the problem of Fermi liquids, it's a very difficult equation to solve if I want to find the correspondence between N, T, and mu. It's usually difficult. Even for this very, very easy case of three energetic levels, we couldn't solve the equation, right? Only in some specific approximation, etc., etc. So the problem is how mu depends on T. I know that mu goes to 0 when T is small. So what? How exactly it goes to 0? So in order then to answer this, I want to use a little bit different approach. Because I know that when I'm looking on the polylogarithmic functions, in the limit when the fugacity is 1, the contributions are negligible. So if I'm working in this region, okay, I can neglect something, but this something it's actually really, really, really small. So therefore, I can say the following thing. I know that for the average N, for T larger than Tc, okay, I know that it equals to G0V divided by lambda T to the third of F 3/2 of the fugacity. This I know. Okay, so what is N0 divided by this N in the limit of T larger than Tc? So what is the contribution in the normal phase? What is the contribution of a single level? If I have many different particles, 0. So this should go to 0. Okay? It's absolutely negligible. Now, let's go to the other limit. What is happening between for T less or equals to Tc? Less or equal to Tc. So you know what? We take the boundary exactly at Tc. What happens exactly at Tc? The average number of particles, it equals to G0V lambda Tc, right? Because I'm working at T equals to Tc, to the third power of F 3/2 of what? 1. Exactly 1. I can say, well, why it's not exactly 1, etc., etc. I'm saying, you're near this point. You neglected something. So it's huge number plus something small. Forget about this something small. It's just f3 halves 1, it's 2.31. Maybe it's 2.31000002. You don't care. Okay. Next step. What happens TU smaller than TC? Now, I know I can compute exactly the average number of particles, not at the lowest level, but at the excited levels. So, n excited average. What is this? It is G0 V lambda t to the third power f 3 halves of what? What is the fugacity in this approximation? Below the critical temperature. What I plug inside over here. Just one, right? We can say because I know that fugacity is really close to 1. It is really close to 1. Okay? For what I care, this number is 2.31 or 32 plus something small. I don't really care what is this something small. Small contribution, I completely forget about it. Okay. So we know, this is what we expect at the high temperatures. This is what we expect for the average number of particles at the critical temperature. This is the excited part. This is the excited part where this is the excited part at the low temperatures. Now, okay, so this is excited, but what is n? What is the average number of particles at low temperature? This is the same average number as it was for the critical temperature, right? Because what's the idea? We bring a lot of particles into the box. We don't let them escape. So we know what's the average number of particles, approximately. It's the same for high temperatures, it's the same for the critical temperature, and it's going to be the same for the low temperatures because this is what we control. We control particles. We do not control chemical potential. So n is G0V lambda Tc to the power 3 f 3 halves of 1. This is what we have. Okay. I remind you, the question, n0 divided by n, the total number of particles, as a function of temperature. So this is the expectation at the high enough temperatures. What happens at the low temperatures?
Wait, didn't we calculate that that's the value of n excited? Is that not neglecting n?
Where? Where?
On the transition from n excited.
Here? Here.
Below at the blue side. We
Of course.
said that n excited is equal to that value.
Yeah.
And isn't it that value plus the n0?
Yes. Yes. Because whatever you have calculated was this with the fugacity. Okay? And the reasoning that we afterwards pursued is that, well, the only additional contribution that we neglected, it's n0. So this is n excited. Okay? Now, what is n0? Can I say that it's just n minus n excited? It's always true. Okay? It's always true. So if I divide it by n and divided this guy by n, okay, what I'm obtaining, that it equals to 1 minus n excited divided by n. Okay, it equals to 1 minus n excited is G0V lambda t to the power 3 f 3 halves of 1 divided by G0V divided to the power lambda TC to the power 3 F 3/2 of 1. And we're getting that it equals to 1 minus lambda TC divided by lambda T to the power of 3. Do you want to remind me what is lambda T?
Something divided by a...
Something
It's basically proportional to 1 over t to the half.
Yes. So, but let's be more concrete. It's a square root of 2 pi h bar squared m k Boltzmann t. Right?
But we don't care about the...
You don't care. Yeah, I absolutely agree with you. I absolutely agree with you. So, but let me be a little bit deductible. So it's 1 minus, and here we have a square root of 2 pi h bar squared divided by m k Boltzmann t c divided by square root of 2 pi h bar divided by m k Boltzmann t. Okay, all of this to the power 3. And finally, we obtain that t lower than tc, n0 average divided by n average equals to 1 minus t divided by tc to the power of 3/2. Okay. And this is a neat result. Is what we obtain as follows. This is n0 average divided by n. This is temperature. This is Tc. And we have, this is 1, and this is 0. Now, the expectation, the naive expectation, is that it should always be 0. Why it should always be 0? Because one single energetic level is always negligible in the continuum limit. And it's indeed a continuum limit if we have a lot of particles over there. It's indeed a continuum limit. But still, somehow, due to this property of the fugacity that shoots up towards this ground state, the ground state takes over, right? So one single energetic level have non-negligible contribution. Now, when I'm saying non-negligible, think of this average n as 10 to the power 23, something like in the Avogadro number. It's huge, huge number of particles sitting all together in the same level. Okay, but you have to cross this critical temperature. So it's a little bit reminds us of what happens to the phase transitions, right? Phase transitions, we had a specific critical temperature. There was one phase, the particles usually were not interacting, it was gas, and suddenly, up, it turned into a liquid where everybody are correlated, or ups, and it turned into a solid, right? So something like this happens over here, but it's very different. There are absolutely no interactions between the particles. But still, this Bose-Einstein condensation, and this is what Bose-Einstein condensation is, appears. Bose-Einstein condensation. Okay. Now, what else can we compute? What happens, for example, to the energy? Right? What happens to the energy? How the energy behaves. Because you can say, Stas, it's very nice that you come here, you describe us this Bose-Einstein condensation as a very physical effect, which describes to you what happens to the number of particles, But in reality, right, when I measure something in my lab, I cannot measure the number of particles. It's not measurable, right? So specifically, it's not that the number of particles is not measurable. I cannot measure the exact number of particles that are sitting at a specific energetic state, energetic level. It's not possible, right? Because I don't know who is who. I don't know where this particle sits, what is the energetic level of this guy and that guy. Okay? So this is the true physics of what happens in the lab. Okay? And in the lab, what we usually operate with, in the macroscopic systems, we operate with energies, heat capacities, stuff like that. A little bit boring, right? Because particles, what happens on the single particle level? That's fascinating. But what happens to the macroscopic quantity like heat capacity is extremely boring. But still, this is what we need to compute. Okay? So we want to go into the limit of define U as a function of temperature, and then let's go to E, and then dE to dt, which is CV. Okay? And this is already measurable quantities. So I'm calling this Bose-Einstein condensation how it was observed. Okay. Let's see. So first of all, I know psi. Psi is whatever, known. What is the connection between the energy, as we know that it is d psi d something. So either it's written in the formula sheet or you have to develop it. So what is this something? So usually I don't remember, but there is always a very simple trick of how to compute it, right? How you compute this something? Sorry? From the probabilities, yes. So, for example, you want to compute epsilon, the average energy at a specific level epsilon. Okay, so what is the contribution, energetic contribution, of a given energetic level epsilon? What is this? This is just average, right? So the average is sigma n goes from 0 to infinity, okay, of what? Of n epsilon multiplied by f of n. Okay. I'm taking a specific energetic level and I'm saying, well, this is the expectation value. What is the expectation value? It's going to depend on how many particles are sitting inside this level, right? So if it's 0, the energetic contribution is 0. If there is 1 particle, the energetic contribution is epsilon. There are 2 particles, 2 epsilons. Since it's average, I have to modify it by the appropriate probabilities, where Fn, remind you, it's 1 over zeta of epsilon of e to the power minus beta n epsilon minus n mu. So let's take it out. Beta n epsilon minus mu. Okay, so what do we do? Yes? E minus mu n. Why? Let's see. Okay, let's see. In a second you will see. Okay. So there are different ways and different formulas. Okay, but everything will be related to this basic quantity. Okay. So either you remember that a specific derivative of the grand canonical potential leads to this or that. Like, for example, what is the average number of particles? It's d psi to d mu with the minus sign. But how we obtain that? Either you remember the transition to the grand canonical potential from E, or you do this. Okay, so what happens over here? So we have E epsilon equals to n goes from 0 to infinity of n epsilon over 1 over z of epsilon e to the power minus beta n epsilon minus mu. Okay? So I can say that this is a summation. N goes from 0 to infinity of n epsilon 1 over z epsilon over here. Here we have e to the power minus beta n epsilon multiplied by e to the power minus beta mu n. Plus. Okay. Now, this guy, I can treat it as a derivative, right? So I have 1 over z epsilon summation of n goes from 0 to infinity of e to the power minus d to d beta of e to the power minus beta n epsilon, and all of this multiplied by e to the power beta mu n. Correct? Okay. Now, I'm saying keep mu beta constant. So if I'm keeping beta mu constant, this guy is minus 1 z epsilon d to d beta summation n goes from 0 to infinity e to the power minus beta n epsilon multiplied by e to the power beta mu n. I can't do that if I'm always considering that beta mu is constant. I'm taking a derivative with beta, but beta mu is constant.
Why can you say that?
Why not?
Because beta and mu are properties of the problem.
It's a mathematical problem now. Can I go from this line to that line under this assumption?
Instead of solving every single problem...
I'm having two hats. One my physicist hat, and the other hat is the mathematician hat. Now, I'm now wearing my mathematician hat, and I'm asking you the following question. Can I do this trick?
If beta mu equals 1 then?
I don't need to.
Oh, you can solve it from up there.
I want to solve it like this. Can I do that?
Sure, of course.
Yes.
I allow it.
Okay, great. We have an assurance that it's fine. Okay, so it is minus 1 over z epsilon d to d beta of what? What is this? No. What is this?
1 over 1 minus e rounds beta mu.
No, it's z epsilon. Right? It's z epsilon. It is z epsilon?
Now it's ln.
Ah, so it is. Keep mu beta constant, keep mu beta constants, minus log of z epsilon. Okay? Minus log of z epsilon, I'm sorry. And here, minus d to d beta. Right?
Yeah, that was what we did in
Okay. So if it's minus d to d beta of log of z epsilon. Okay. So e epsilon equals minus d to d beta of log of what? Of z epsilon. Now, sum everything up. Can I do that? Why not? I'm still in my mathematician head. Okay. So this is the guy that we wanted to compute. E. Here, we can switch the derivative of with respect to beta and the summation. So it's minus d to d beta summation over epsilon log of z epsilon. Right? Okay. So what is a summation of log of z epsilon? What is this?
Log of the product of the z epsilons.
So here I will, yes, of course, but I want to do something different. I want to do it something else. I want to say the following thing, is that if I take this, I divide it by beta, and I put a minus over here. What is this quantity?
The grand canonical potential.
The entire system.
Right? It's always, this is how we found it. This is how we found the grand canonical potential out of this sum. And then, instead of summing everything up, we went to the integration. Okay? So, what we have is that E equals minus d to d beta of what? Minus beta psi. Or, the final answer is that, remember, d psi to d something? Oh, here are something. Oh, it's not exactly d psi. E equals to d beta of beta psi, keep mu beta constant when you take all the derivatives.
Mu times beta is a constant, but b itself doesn't have to be a constant.
Mathematician hat. I'm taking the derivatives, and during my derivatives, every time I see beta multiplied by mu, I'm saying, oh, it's a constant. Okay? I finish up my derivatives, I take my mathematician hat and say, oh, I have the expression of E.
And would it also work when beta mu is not constant?
No, it won't.
Oh, but most people probably don't.
No! Mathematician hat. When you take the derivative,
And
only during this process, how I take the derivative, during this derivative, because, look, it's a trick to go from here to here.
Sure, but you want to
It's a trick.
But you want to describe problems, and most problems won't have this property.
All the problems are going to have exactly this property.
Okay.
All the problems. Because during the problem, you take the mathematician hat, you say, now I'm doing this trick, and then you take it off, and it's fine.
So is there some like approximation that means that beta mu is a constant? Is
No, you don't need this. It's not approximation.
But is there like a physical meaning?
No.
Okay.
No. It's a mathematical trick
Okay.
in order to sum things up.
Sure.
The thing is, and this is a mathematical property, if a sum is converging, it doesn't matter how you found this limit of convergence. Okay? If the sum is converging, it doesn't matter how you summed it. Okay?
But you just said it won't work if beta mu is not.
No, this trick won't work.
Okay.
I found a trick to sum this to describe to you what is the sum is.
Okay.
Since the sum is converging, and this is a physical assumption because you can say stas, it's not converging, then it won't work. Okay? But if a sum is converging, it doesn't matter how I found the limit. Okay? If it's diverging, oh, this is a whole new world. Not for this lecture. Because, not for this lecture. For being a summation, earlier summation. Nice thing. All right, so this is what we have, right? This is the energy. I don't have a lot of time, but what I have to do now is to say, oh, great, because I know what psi is, right? So what is psi?
You have the before TC and after.
Great. Let's see. So we have two limits. Okay. So psi is what it was? I forgot. Forgot the psi, what it was our psi. I remember the n. Okay, so it was, could it be? I don't have it any. 2/3. So I have G0 V lambda T to the third K Boltzmann T. Yeah, sounds okay. 5 F of 5/2 of the fugacity. Remember, what is the fugacity? What is the fugacity?
E to the power beta.
E to the power beta mu. So fugacity is constant. Yep. There is no other b mu inside beta mu inside this expression.
But there was the constant in respect to mu. It could be not constant in respect to beta.
Ah, it's interesting. Let's neglect it for a second. And I'll describe you later why it's not important. Okay. Now, what we have over here is, let's take this. So E equals to d to d beta of what? Of beta psi. So it is 1 over K Boltzmann T minus G0 V lambda T to the third K Boltzmann T F 5/2 of the fugacity. Now, when I keep this, I say fugacity is constant. Fugacity is constant. Keep Z constant. Okay? Okay, so K Boltzmann T and K Boltzmann T, they cancel out. And finally, what I obtain is that E equals to 3/2 K Boltzmann T G0 V divided by lambda T to the third power F 5/2 of the fugacity. You take the derivative of lambda T, and that's what appears out of this. You want to make it explicit? The only thing that you have to take the derivative of is this lambda T over here. Right? So remember, what is d to d beta? It is d to d t multiplied by 1 over what? D t to respect to d beta, right? You use this formula and this is what you obtain. Okay? So basically the only thing that you have to take take a derivative of is this lambda T to the third power. Okay, so where is my okay. So let's try and see what we managed to do so far. I want to describe this in the following sense. So I have E, which is 3/2 K Boltzmann T, G0 V divided by lambda T to the third power, F 5/2 of the fugacity. I know that unexcited average, it is G0 V divided by lambda T to the third power, F 3/2 of the fugacity. Okay. Now, I can plug everything, this unexcited, inside this guy over here. Because you see, if I take this and I multiply it and divide it, so I multiply it by what? By F 3/2 to the xi divided by F 3/2 to the xi, right? I obtain that E equals 3/2 K Boltzmann T, okay, multiplied by unexcited average Okay? And there is a prefactor, f 5 halves to the c, f 3 halves to the c. Which is reasonable, right? Why it's reasonable? Well, the only particles that I care of, are particles that are sitting in the excited states. Because particles that are sitting at the ground state, their energy is 0. They're not contributing. So the only thing that is contributing is the number of particles that sits over here. Now, here it's a trick. Why it's a trick? Because, think of it. If I haven't had this part over here, right? This prefactor with the ugly polylogarithmic functions. Okay? What I have a gas of particles. Okay? The particles are not interacting. Absolutely not interacting. They're spread up inside this energetic levels. So what? There is only kinetic energy. So it's a gas of non-interacting particles. Ideal gas, non-interacting ideal gas. What should be the energy of the non-interacting ideal gas? 3/2 K Boltzmann T. Why 3/2? Because we, in three-dimensional. Okay, K Boltzmann T. Multiply the number of particles. Excited, not excited, who cares, right? There is a prefactor. This comes from the quantum statistics, right? And also the excited also comes from the exact form from the quantum statistics, right? We can compute this. We can compute this in the two different limits. And an interesting fact occurs. So first of all, I won't show it because I don't have time, but I will just tell you that when T is larger than Tc, what we expect at high temperatures. Sorry? Classical limit. So in the high temperature, when you take those guys, you do it properly, f 5/2 to the f 3/2, this and this goes to 1. This is the classical limit. It exactly happens over here. Okay? So for large temperatures, E equals to 3/2 K Boltzmann T, and excited, it equals to exactly the average number of particles. So we obtain our classical limit as expected. Now, what happens to the other limit? When T is smaller than Tc. You can work also exactly at Tc because, well, we know what this guy is and we can compute this numerically. But what happens? For T smaller than Tc, what we assume, at least in those functions, that the fugacity is exactly 1. Right? So for T smaller than Tc equals 3/2 K Boltzmann T and excited, okay, multiplied by f 5/2 of 1 divided by f 3/2 of 1. So it's a constant number. Okay. But what is unexcited? Oh. So unexcited, what we know? We know that n minus unexcited, excited, divided by n. We have shown this for T smaller than Tc. It equals to 1 minus T divided by Tc to the power of 3/2. Okay, so we have 1 minus n excited divided by the average number of particles equals to 1 minus T divided by Tc to the power of 3/2. So n excited average equals to n multiplied by t divided by tc to the power 3/2. Okay, let's plug it inside. And we obtain that E equals to 3/2 k Boltzmann T, okay, multiplied by the average number of particles. This is the classical stuff. Everything is fine, but we have this addition due to quantum properties. And this addition is T divided by Tc to the power of 3/2 multiplied by F 5/2 of 1 divided by F 3/2 of 1. Classical limit, quantum complications. So if we plug this, wait a second. Plug this. So we plug the energy as a function of temperature. We obtain that it rises up like this. And then, so this happens exactly dc. Then it goes to something like this. This line over here is 3/2 n k Boltzmann. Okay, so there is something happens over here. Yes, question.
This is like t smaller than this.
No.
Okay.
No. Because you can make this approximation at any temperature for T smaller than Tc.
Okay. Yeah.
Okay? There are additional small something over here, but you don't care. Okay, so this is E. I have almost no time now because, well, we still do not measure energy, right? Okay, so there was something interesting that happens to the average number of particles. Something interesting happens to the energy. What people actually measured and how all of this business started. Okay? What they measured is the heat capacity. So what is the heat capacity? Of this guy. Yeah? So
But you can assume that the N is quite a constant in the...
no, because it's an excited. And an excited, it's not quite constant. It's an excited. Okay? It's not. So what is CV? And when you take the derivative with T, you have this ugly part. Right? This is ugly because it depends on the fugacity. And fugacity for temperatures that are larger than Tc, it's not 1. It's e to the power beta mu. Okay, so I can write it down as d to dt of what we have of E equals to d to dt of 3/2 k Boltzmann t. And here I have n excited multiplied by f 5/2 e to the power mu divided by k Boltzmann t, f 3/2 of e to the power mu divided by k Boltzmann t. Okay? Now you don't have any magic tricks over here. You have to take the derivative and see what happens over here, and etc., etc., etc. Okay? I will write down to you what happens eventually. Okay? What happens eventually, because n excited is g0v lambda t to the 3, and here we have what we had, f 3/2 of e to the power mu divided by k Boltzmann t. Okay, so you have to take something which is ugly of this polylogarithmic function, and after you do everything, after you do all of this, you obtain two limits. It's ugly derivative. It takes a lot of time. So CV for t smaller than tc, CV equals to 1.9 the total number of particles, k Boltzmann, and again t divided by tc to the power 3/2. Okay. For t larger than tc, we can make some sort of approximation. So what is the expectation in the classical limit? Why?
Because it approaches an ideal gap.
What's the name of the theorem? Equipartition theorem should work. Okay, high temperatures equipartition theorem should work. We have independent particles, independent degrees of freedom. They have only kinetic energy, so it's always, and if you take the derivative of this nasty thing, this is what you obtain, that CV equals to 3/2 n k Boltzmann without t. Okay, so, and the transition, and this is how this started. This is CV, this is T. And it looks like this. TC, it goes up, and then it goes down. Somehow, it reminds people of the Greek letter lambda. So this is why it's called lambda transition. But the interesting part is that the heat capacity in the vicinity of this T critical goes down. Right? Three halves and k Boltzmann. This was what measured. This is where we obtained it from. But the physical reason for all of this is the occupation of the ground state level. So N0 divided by the total number of particles as a function of temperature has this fantastic form. Here the true physics lies, because I can say, well, it's just a curve with something peculiar over here. It is another curve, well, lambda curve, okay, with a chupchik over here, right? A cusp. But the physics comes from here. For high temperatures, it's zero. Negligible contribution of a single energetic level. For low temperatures, it's not negligible. Right? It's counterintuitive, but this is the physics. There are situations, there are phases, okay, where the contribution of the one oversums the contribution of the many. Okay, that's what's important. Okay, that's it. And next lecture we start modern phase transitions and Ising model. See you all next week. אני חושב או השבוע הזה, מחר, ולא אמרתי אז אני לא יודע, או שבוע הבא. כן.